Dear students, today in this video we are going to discuss about the regular space and some of the results regarding the regular space. First of all, what is the definition of a regular space? Regular space. Suppose you take a topological space, X tau, in which each singleton point is closed in that space. And further that, you can take any point X and a closed set B not containing X. That is, given a point X and a closed set not containing the given point X. Suppose there are neighborhoods U and B of the point X and the set B such that U intersection B is equal to empty. Then the space is said to be regular. That is, in order that space to be regular, the space must obey the following conditions. Each singleton point is closed in that space, and then given any X and a closed set not containing the point X, there are neighborhoods U of X and V of B. That is, neighborhood of B means that it is an open set containing the set B. Okay. So there are neighborhoods U and V of X and B respectively, such that U intersection V is empty. That means, given a point and a closed set not containing the point, they can be separated by means of adjoining open sets. Such a space is referred as a regular space. So there are plenty of examples for regular space. So before proceed into the examples, we shall look at some important results, which would be useful to discuss about the examples of a regular space. Not only that, there are many theoretical background regarding the regular space, but for the moment we just define a regular space, and we are going to prove that various results pertaining to this regular space. So one fact is obvious, that is, a subspace of a regular space is regular. So we know in the earlier classes we have defined what is meant by a subspace of a topological space. Now also we proved that if a space is Hausdorff, then its subspace is also a Hausdorff space. Now we are going to prove a similar result. If you assume that the space is regular, then its subspace is also a regular space. For that, you take a topological space which is regular. You take a topological space X which is a regular space, and you consider a subspace Y of X. Y a subspace of X. To prove that Y is also a regular space. Y is also a regular space. The first condition is, in Y, every singleton set is closed. For that, you start with the arbitrary point Y in capital Y. You consider the single point set, that is singleton Y. Being a point of Y and Y is a subspace of X, Y is also a point of X. And here X is a regular space, therefore every single point is closed in X. Therefore, first we get the result that Y is closed, singleton Y is closed in X. you take that singleton y, a closed subset of x, intersect with y, okay, you will obtain the single point y. Okay, you will obtain single point y. Now note that here we write the singleton y as a closed set in x, intersect with y. In other classes we have discussed that set is closed in y if and only if it can be written as, okay, y intersection some closed subset of x. So here we write exactly the singleton y as some closed set, namely the singleton y, closed set in x, intersect with y. Therefore, singleton y is closed in y. Because we have chosen that y as an arbitrary point of the space capital Y, now it follows that every single point set is closed in y. The first condition for the space y to be regular is satisfied. Okay. What is the second one? So given any point of y and a closed set in y not containing the point, those two can be separated by means of disjoint closed sets in y. Okay. You consider arbitrary point y x in y and a closed set say, okay, closed set say b in y. And assume that x not in b. That is, we have taken arbitrary point x and a closed set in y which is not contained in the given point x. We are trying to establish neighborhoods in y, one containing x, the other containing the set b, whose intersection is empty. First of all, this point already, a point of y means that it is point of x, no problem at all. Here the set is closed in y, therefore, okay, the set is closed in y, therefore its closure in y, that is closure of the set, closure of b maybe with respect to the space y equals the set b. Okay. Here the obvious facts are b subset of y. We are dealing with a subspace, therefore b subset of y. A closed y means that its closure with respect to the space equals itself. Okay. But according to previous result, we have proved that a closure of the subset in a subspace can be written as, okay, y intersection closure of the same set in relation to the whole set, where the subspace topology is inherited. Okay. So closure of the set B with respect to y is closure of the same set B with respect to the space X intersect with y. That is a characterization theorem for finding a closure. Okay. Or it is some substitution addition, or you may take that. Okay. So I have this representation for the set of B. Okay. It x not in B, but already a point of y. X not in B, already a point of y, therefore x not in B closure. And observe that B closure is always closed in X. Because closure of the set is always closed in any topological space. So look at that, here we are having a closed set in X and a point not in the closed set, whereas the space X is a regular space. So you apply the definition, okay. Here is a point and a closed set not contained in the point, therefore there are neighborhoods, okay. There are open sets, say U and V in X. Okay, this word is somewhat important. In X, such that what are the things that U and V have? What are the facts? X belongs to U, B closure subset of V, and U intersection V is empty. Okay. You take these open sets intersect with Y, you are getting open sets in Y. Basic definition of a subspace. Okay. Topology of a subspace. You take U intersection Y. So here you may find that X is a point of U, already a point of Y, therefore X is a point of U intersection Y. So you name it as U1. You name it as U1. So U1 is an open set in Y containing the point X. And then similarly you are having V intersection Y. This obviously contains the set B closure. This set B closure. Okay. Intersection Y. Because your B closure already subset of V, and if you take B closure intersection Y, that is your B. That is your B. So you name it this set as V1. So V1 is, and U1 and V1 are now open in Y. Because you are taking U intersection Y and V intersection Y, with U intersection V is empty, we leave that U1 and V1 are disjoint. So what are the things we are getting? So open sets U1 and V1 which are disjoint, U1 containing the point X and V1 contains the set B. Okay. That means these two pair, that is a point in Y and a closure in Y not containing the point, can be separated by means of disjoint open sets. Because we have chosen this point and the closure not containing the point in Y as arbitrary. Okay. This is true for every such pair, which means that your Y becomes a regular space. Already we have proved that every single point set in Y is closed in Y. Now we establish the fact that given any point in Y and a closure in Y which is not containing the given point, they can be separated by means of disjoint open sets. So these two together proves that Y is also a regular space. Okay. I hope you understand this small result. Okay. We can prove subsequent results one by one in the next videos. Thank you.